So thank you very much for inviting me to give this keynote about capturing, analyzing, and reacting on IoT-generated sensor data in real time. So why is everybody talking about IoT at the moment? I've seen the agenda, and I think nearly 50% of all talks are about IoT. So last year we had 15 billion connected devices. And in 2020, it is predicted that we have 40 billion connected devices on the planet. And in contrast to our world population this year, 7.4 billion, this is quite a lot. So 90% of all data generated is at the edge of an IoT device. And this data is never captured, never analyzed, and never acted on. And 60% of all data loses its value within milliseconds. And in addition, a new generation of sensors is evolving. They are low cost, they are low on energy consumption, low on data transmission cost, and they have long life batteries, and they are self-supplementary, for example with solar cells. That's an example of such a sensor. That's a humidity sensor manufactured by a company called Sensirion in Switzerland, and it costs $5, and it really consumes nearly nothing of energy. There is a battery, costs $2, and there is a gateway device costing $50 and has a range of 800 meters. And with that battery, you can power that compound for 70 days. So you see, the technology is already there. And IBM said, okay, if a tree falls in the forest, we want to hear that. Therefore, IBM announced last year to create the IBM Watson IoT unit and will invest $3 billion, and that IBM Watson IoT global headquarters will be in Munich. And as of 2015, we already have 4,000 IoT clients in 170 countries. We are partnering with 1,400 partners already. We will see 2 of them later. And we own 750 IoT patents, and currently we have 1,000 employees only in the headquarters in Munich. So one partner is Siemens, building technology division to maximize the potential of connected buildings. And in my opinion, it's mainly because of the data we are capturing here. And as you can see in that illustration, it's beyond that you turn off the AC if somebody leaves the window open. But already that would save so much money and so much energy that you can see the potential of such a system is really high. And another partner we have is KONE. It's a Nordics-based elevator manufacturer. And I've seen that in the news in Dubai. There was an outage of an elevator, and this caused a shock for the tourists and also bad news. And the idea is in IoT connected elevator, the elevator itself can notify you that he hears something which is unusual. And then you don't have to stick to the already planned maintenance cycles. You can send somebody there. And of course, if the elevator thinks he's okay, you don't have to send somebody there. That's the basic idea about that. How do we do IoT? So the central protocol there is MQTT. And MQTT is a lightweight telemetry protocol. It's published, subscribed, enabled once you're using it through a message broker. It was invented by IBM in 1999 and became an OASIS standard 2013. And the message broker IBM uses is called a message site. And this basically is an appliance. And since we don't want our clients to maintain such appliances, we offer this as a cloud services, and we call this the IBM Watson IoT platform, which is at the heart MQTT broker. And what we then also deliver are APIs for devices, more than 200 at the moment, and this number is weekly increasing. And that's a simple example of a Raspberry Pi connected to a SenSet sensor device, which has some sensors like humidity, temperature, accelerometers, and also some actors like these LEDs. And as you can see here, you have to write 6 lines of Python code to initialize the system, and then you have to write 3 lines to send a temperature value to the cloud. And you can specify quality of service 2, which means it's a guaranteed delivery. So you don't have to care about anything else like connecting usernames, passwords, outages, fault tolerance, and so on. That's all done for you. And if you're interested in doing that yourself, we will launch next month a Coursera course on that. And actually, IBM is the first non-academic institution which will launch a Coursera course. And I'm a teaching assistant there, so if you do the course, we will hear from each other again. So what we now have is the central nervous system of IoT, but of course what is missing is the brain. So I will talk about the brain now only. The state-of-the-art cloud-based analytics, what we see at our clients is ApacheSpark. So at the bottom you have to have some high-performance servers. You have to have some storage system. So we use either OpenStack Swift, Hadoop HDFS, or IBM GPFS. And on top of that, you have to have executors. So these are Spark executors, and then some sort of resource management. Either you use open source Yarn or you use IBM Platform Symphony. And then you have these components on top. So with these components, you can do classical machine learning, either on historic data or you do online learning. Both ways can be used for real-time data analytics, but they have both advantages and disadvantages. So based on the problem you have to either choose online or the historic way of doing machine learning. So that's all possible at the moment, but we want to do something else. We want to make the system more intelligent, so we want to use deep learning. And deep learning might be another buzzword, but if it is a buzzword, the hype is not flattening. So as you can see on the Google Trend charts, the hype seems to be flattening on ApacheSpark and definitely on Hadoop. But on deep learning, it's still increasing, and it's a very steep curve. So who of you knows how a neural network works? Okay, some. So I will just introduce that very quickly. So basically, that's also supervised machine learning component. Let's assume you have a training data set of customer churn information, and you have 3 properties of that customers. One is age, one is gender, and one is the yearly turnover. And you want to predict churn, yes or no. So you have the 3 input neurons and 2 output neurons. And what you basically do is you train this neural network with all your data, and at the end of the day you will adjust these parameters of the neural network, and the neural network plus the parameters will deliver you a predictor. So if you have a new customer, you don't know the churn probability, you just input these 3 features, and at the end of the day, the neural network will tell you the churn probability. So by deep learning, you can increase the number of hidden layers between input and output, and that basically means that you have a higher abstraction. So from left to right, the abstraction decreases and will be more concrete. And first application where this really took off is convolutional neural networks for image classification. So as you can see here at the bottom, the layers near to the input are very abstract. They only recognize lines. And the more you go to the output layer, the more concrete are the neurons firing on certain input. And if you are really near to the output layer, you see already the concept of faces, cars, elephants, and chairs. Such a network can be used to actually turn it to a generative model. So you can train such a network with a style on the left-hand side. You can use a concrete image. That's a profile picture of myself. And then you apply the style on the picture by reading the image with a already trained convolutional network, and the output is something like you see here. And this can be pushed even further. You see here the picture of the Golden Gate Bridge, and then you see different artistic styles, and then you see what the neural network actually generated. And we have a Swiss-based partner. He actually is running on our cloud, and he uses this as a business model. So what you can do with those types of neural networks, these are feed-forward networks, you can learn any mathematical function given enough data. So you don't have to know the details of the system you observe, you just have to collect enough data, and then you can generate a function behaving like the system you observe. So let's add some additional connections into the neural network. You can add feedback loops, and then you have a recurrent neural network, and that neural network is actually capable of recognizing patterns in time series because it has now short time memory because of the feedback loops. But short time memory sometimes is not enough, so you can add another component which then turns this recurrent network into a long short time memory network. And it has memory inside it, and it also forgets, and this forgetting parameter is also learned. So you have to, while training, you have to learn the parameter on how much information you basically forget. And here's an example of such long short time memory neural network used as a generative model. So this network has been trained with Shakespeare literature. Without knowing about English, without knowing about words or the concept of sentences, it was able to generate this text. And you see, it's at least looking like Shakespeare. It can also learn and generate scientific literature. And it can also learn and generate C source code by looking at the Linux kernel source code, learning how the Linux kernel source code looks like, and then generating this source code. It doesn't compile, but it's not missing a lot. So you can see you can use a neural network to generate other programs. And you can use a neural network to compose music by letting the neural network listen to music. So let's see how this works. So this hasn't been composed by a human, this is composed by a neural network. And the neural network learned how to compose by listening to classic music. And here's a publication from last year where they used a long short-term memory network in order to do anomaly detection in time series. And they really proved that it works. So they outperformed traditional methods. And the network basically learned what normal is. And if the network saw unusual time series patterns, then it raised an error. Or for every sequence in the time series, it basically calculated the error between the data it already has seen. So long short-time memory network is basically Turing complete. Okay? That means if you have enough data, you can stop programming because the network will learn how to do it. It can do everything what a normal computer can do. So there are a couple of problems. So they are very computationally intensive, and especially during training. But there is some hope. So 2009, Google built a neural network of the size of a bee. It has had 1 million neurons on 16,000 CPU cores. It was a very expensive neural network. But the same power you have now in a $500 NVIDIA Titan GPU card. And in 2 years, IBM will release a ASIC, application-specific processor, which basically can execute a neural network. So you train a network, and then you can flash it to the ASIC, and then it behaves like a neural network, but all the computation is done in silico. And you have seen the state of the art, and now this is the future. So there are deep learning libraries on top of ApacheSpark. One is deep learning for J, and one is H2O. And they support GPUs, and they support the vector units of modern CPUs. So if you add that to that ecosystem, and you install a couple of extensions to the Linux kernel and install a bit of software in addition, then you can use the GPUs and the vector extensions of the CPUs just without knowing it. And that's basically the architecture we are proposing, and I'm currently writing this up in an article which I will publish soon. So the formal definition of IoT, in my opinion, is cognitive IoT, maximizes efficiency of the system under observation by measuring all relevant parameters in order to react accordingly to push the whole system into a state nearer to the global optimum. And my vision is the following. So what if the majority of all cars were connected and sensed? What if we could detect a state of an unpreventable accident? And if we detect that, we just issue a command to all cars, please brake with 30% force. Then we could prevent the accident. So that's my dream. Let's see if it will happen. So that's my last slide. You can do all you have seen today yourself. As I already told, I will publish an article on how to do this on IBM Developer Works, and I will announce it on my Twitter account. This will happen in 2 or 3 weeks. And this talk I've recorded, so you will be able to watch it on YouTube. And in case you have any further questions, please let me know. Yeah, so the thing why I've shown you this neural net art and the piano thing is in order to convince you that neural networks are very powerful in learning patterns from data. That's all. And since we have a lot of data in IoT, in my opinion, we should apply them in IoT. So the current state of the art is support vector machines and random forests and all that stuff. But we are really at the beginning of deep learning, but I have the feeling we should dive deeper into that research because the potential is just immense. I would say the deep neural networks, and what I see is that the long short-time memory networks, they are performing really, really well. And I think we have there to solve the computational challenges and also the training, because all the networks currently are trained using web propagation, but there might be more efficient ways of training such a neural network, and that's research which has to be done.
Don't you think there might be a problem if you overtrain?
Yeah, the addressing of the overfitting problem is also part of the deep learning hype. So there are new algorithms to address the overfitting problem. One famous is called dropout, which basically on each learning cycle just deactivates 50% of your neurons. That means the neural network has to find alternative paths through the neurons for giving the same result. And there are other methods like L2 and L3 regularization and other algorithms in order to address the overfitting problem. So
On the train, when you train not enough.
neural networks, in my experience, mostly have the overfitting problem. If it's undertrained, then you have a data problem. Either your data is not good or you have not enough training data. And yeah, there's another like rule of thumb. You need to have 10 times more data than you have degrees of freedom in your system. And that's actually a problem with neural networks, because as you can see in such a network, every neuron has a couple of parameters. And if you have like 1,000,000 of neurons and 10 parameters per neuron, you have 10 million parameters or degrees of freedom. That means you need at least 100 million of training examples for such a network. Okay? Yeah?
The computational is very costly in terms of such a deep learning. In terms of, when we talk about Internet of Things and 5G, we want instance response. Have you compared with some technologies that improve that you can provide this timely information?
Yeah. So I haven't formally proved anything, but I can tell you two promising projects. One is BlinkDB. BlinkDB is a database where you actually define either the accuracy of the result you need, let's say 3 or 5 or 10% accuracy, or you define the response time. And you say, okay, I need this result within 100 milliseconds, and then the accuracy decreases. So that's one thing you should have a look at, BlinkDB. And the other one is technologies like this ASIC. I have to go back. This Synapse project, because that's fast. So once you have trained the model, you can push the model to any IoT device, and then you can react in milliseconds.